Hi, good afternoon. My name is Anselm Aranya, BEC third year session R. So I'm here with you again to discuss my answer in plate number 12, which is all about the design of the reinforcement concrete of isolated footings. So I'm assigned in part 2, number 2. So please be with me as I answer the problem. Thank you. Part 2, number 2 states that design a rectangular column footing to carry from the following loads. The column size is 450 times 450 millimeter and the reinforced bar is 8 pieces of the 25 millimeter. The actual load, the dead load is 850 kilonewton and the live load is 750 kilonewton. The moment MDL is equal to 250 kilonewton meter, MLL is equal to 210 kilonewton meter. The depth of the footing is 1.5 below the natural grade, with the width of footing is limited to 1.8 meter. The allowable soil pressure is 320 kilopascal. The unit weights of the concrete is 23.5 kilonewton over cubic meter. The unit weight of the soil is 18 kilonewton over cubic meter. The concrete compressive strength is 28 megapascal and the steel yield strength is equal to 450 megapascal. The main bar diameter is 20 millimeter and the concrete cover is 75 millimeter. So this is the figure of the column size, which is 450 times 450 millimeter, and then we will assume that the total depth of footing, which is HC, is equal to 0.8 meter. Then the HS, which is the height of the soil above the footing, is 1.5 minus 0.8. So our HS now is equal to 0.7 meter. Then we proceed to in finding the size of the footing. So to find the size of footing, we will need to use this equation, the effective soil bearing capacity, which has QA minus YCHC minus the unit weight of the soil times the total depth of the footing. So substitute the allowable soil bearing capacity is 320 minus the unit weight of the concrete is equal to 23.5 times the total depth of the footing, which is 0.8, minus the unit weight of the soil, which is 18 from the problem, and the HS, which is 0.7, the height of the soil above the footing. So our effective soil bearing capacity is equal to 288.6 kilopascal. Then to find the length of the footing, we need to use this formula, which is the area of the footing is equals to the dead load plus the live load over the effective soil pressure. So equate 1.8, which is the width of the footing, times length is equals to the dead load of 850 and the live load of 750 over the effective soil bearing capacity, which is 288.6. So our length now is 3.1 meter. We proceed to the thickness of the footing, which is, we need to use this formula. PU is equal to 1.6 times the dead load plus 1.6 times the live load, which is, PU is a factored bearing capacity. Then we substitute the dead load and the live load. So 1.2 times 850 plus 1.6 times 750. Our factored bearing pressure now is 220 kilonewton. Then we proceed in finding the ultimate soil bearing strength, which has the formula of QU is equals to PU times the width of the footing times the length of the footing. So equate, our PU is 2,220 kilonewton over the width of the footing, which is 1.8 times 3.1, the length of the footing. So our QU is equals to 397.85 kilopascal. Now we proceed to the one-way shear on the short side, which has the correction factor of 0.75. So this is the figure. So the distance from here to here is 1.325 because 3 minus 1 minus 0.5 divided 2 is equal to 1.325, and this our distance from this one, the broken line, can be 1.325 minus d. So our width is 1.8, or is equal to 1800 millimeter. So the depth based on the wide beam shear, we use the VU, or the factored shear force, that has the formula of QU times the width times the distance from here, the 1.325 minus d. So substitute VU is equal to the ultimate soil bearing stress, or QU, which is 0.39785 from the previous solution, times the width is equal to 1800 times the 1325 minus d. So our factored shear force is 716.13 times 1325 minus d. Proceed to the finding of VC, or the shear strength, that has a formula of 0.17 times the compressive force that is given in the problem times the width and the d. So substitute 0.17 times the square root of 28 times 1800, which is the depth, the width and the d. So our shear strength is 1619.2 d, and we equate the VU is equals to the correction factor, which is 0.75 times the shear strength, to find the d. So substitute the 716.13 times 1325 minus d, the factored shear force is equals to 0.75, the correction factor, times the 1619.2 d, the shear strength. So RD is equals to 491.51 millimeter. And we proceed to two-way, or the punching shear, or the depth based on the punching shear. So the BO, that has the formula of 4 times the side of the column, which is 450 plus d. So our VU, or the factored shear force, is equals to VU equals QU times the width of the footing times the length minus the BO. So substitute our QU is 0.39785 times the width of the footing and the length, which is 1800 times 3100 minus the BO, which is 450 plus d squared. Our answer of the factored shear force is 0.39785 times 558 times 10 raised to the power 4 minus 450 plus d squared. So we proceed to the shear strength, which has the formula of 1/3 times the compressive force times the BO d. So equate 1/3 times the compressive force of 28 FC prime times the BO, which is 4 times 450 plus d times d. So our VC is equals to 1.76 times 4 times 450 plus D times D. So to find the D, we need to equate the two equation. The VU is equals to the correction factor VC. So substitute 0.39785 times 558 times 10 raised to the power of 4 minus 450 times D squared is equals to the correction factor of 0.75 times the shear strength or the VC 1.76 times 4 times 450 plus D times D. So RD is equals to 418.6 millimeter, and we will use the one-way shear D, which is 491.51 millimeter, or koan D is equals to 492 millimeter. So the steel requirement of footing, so let's start with the formula of the HC, which is the total depth is equals to D plus the 1.5 diameter of the steel bar plus the cover. So substitute RD is 492 millimeter plus 1.5 times the given diameter of the steel bar, which is 20, plus the steel cover of 75 equals 597. So 597 is lesser than the our assumption of the total depth, which is 800. So means it is okay. So so steel requirement. So to find the D, we need to use this equation from this figure. So we get the 0.325 by 3 minus 1 minus 0.45 divided by 2, that is equal to 0.325. So substitute the D, which is 492 plus 15 times the 20 diameter of the steel bar, which is equals to 522. So our D prime is equals to 522 millimeter, and RB is 1.8 meter or 1,800 millimeter. And we proceed in finding the maximum moment of all forces from a footing, which is MU, that has a formula of QU times 1.8, which is the B, times 1.325, the distance from here, times 1.325 divided by 2. So substitute the QU. Our maximum moment from all forces on a footing is 628.63 kilonewton meter. To find Rn, or the concrete beam design ratio, we need to use this equation. So mu is equals to the correction factor times the concrete beam design ratio, which is Rn BD squared. So substitute the mu, which is 628.63 times 10 raised to the power of 6 is equals to 0.10, which is the correction factor, times the Rn, which is the missing one, times the width of 1,800 times 522 squared. So our Rn, or the concrete beam design ratio, is equals to 1.424 megapascal. Then we proceed in finding the phi, which is the reinforcement ratio, that has a formula of 0.85 FC prime, or the compressive strength, times Fy times 1 minus square root of 1 minus 2 Rn over 0.85 FC prime. So substitute 0.85 times 28 over 415, that is given in a problem, times 1 minus the square root of 1 minus 2. Substitute the concrete beam design ratio, or the Rn, 1.424 times over 0.55 times 28. So our phi is equal to 0.0035. Next, we proceed to the equation of the area of the steel reinforcement, which is ES, that is the formula of the phi times BWT. So i-equate ang mga value. So our fee is 0.0035 times the width of 1800 millimeter times our D, which is 522. So our area of the steel reinforcement is 3,288.6 millimeters squared. And in finding the number of steel bars, we need to use this equation, which is N is equals to the area of the steel reinforcement over the area of the steel bar, which is, to substitute the AS, which we have 3,288.6 millimeters squared, over pi over 4 times the diameter of the steel bar, which is 20 squared. So we have 10.46, and let's say it is 11 pieces of the 20 millimeter bar, 20 diameter. And to find the top bars in a short direction, which is this figure, so we start in the maximum moment from all forces on a footing, which is mu. So substitute the given value. So our QU is 397.85 times the measurement from here, which is 3.1, times the 0.675, the distance from here to here, times 0.675 over 2. So our maximum moment from all forces on a footing is 280.97 kilonewton meter. Then we proceed in this equation. The mu is equals to the correction factor, Rn BD squared. So substitute the 280.97 times 10 raised to the power of 6 times the correction factor of 0.9 Rn times the length, the width, which is 3,100, times the D of 492 squared. So our Rn is equals to 0.416 megapascal. And we proceed in finding the phi, that has the formula of 0.85 Fc prime times Fc prime over Fy times minus the square root of minus 1 minus 2 Rn over 0.85 Fc prime. So substitute the Fc and the Rn. So we have the equation of 0.85 times the Fc prime of 28 over the Fy, which is 415, times 1 minus the square root of 1 minus 2. Substitute the Rn, which is 0.416 over 0.85 times 28, which is the Fc. So our phi is 0.001, and we have the phi mean. So the formula of phi mean is equals to 1.4 over the Fy. So substitute the Fy, which is 415. So 1.4 divide 415 is equals to 0.0033. So we use this in this formula, which is the P mean from here, the phi. So the area of the steel reinforcement, the top bars, so ES is equals to phi times the width and the diameter. So equals the P mean 0.0033 times the width 3 times 3,100 times 492. So our area of the steel reinforcement is 5,033.16 millimeters squared. So in a bar distribution, the center bandwidth, we have the formula of the long side of footing divide the short side of footing. So the 3.1 and the 1.8. So our coating factor is 1.72. And we proceed in this equation. We equate the area of steel reinforcement center band over the total of the area of the steel reinforcement equals 2 divide the beta plus 1. So substitute our area of the steel reinforcement is 5,033.16, and is equals to 2 point r beta, which is 1.72 plus 1, 1.72 r beta plus 1. So our area of steel reinforcement center band is equals to 3,700.85 millimeters squared, and the number of steel reinforcement or in the top bars, we need to use this equation or the formula. So substitute n is equals to the 3,700.85, which is the area of the steel reinforcement of the top bars, divide the area of the steel, which is pi over 4 times the diameter of 20 squared. So we have 11.75 millimeter. So let's say it is 12 pieces of the 20 millimeter diameter steel bars. So the outside center bandwidth, so we have the formula of ESO is equals to the ES, or the area of the reinforcement minus the area of reinforcement of the center band divide 2. So substitute the value from the previous solution. So the area of the steel reinforcement is 5,033.16 minus our area of the steel reinforcement of the center band, which is 3,700.85 all over 2. So our outside center band is 66.155 millimeters squared. So the number of the center band steel bars, so we need to use this formula again, the 666.155 divide the area of the steel bars that has the diameter of 20 squared. So we have 2.1. So let's say it is a 3 pieces of 20 millimeter diameter of the steel bar. And now let us check the development length to determine if the hook at the end is required. So the required development length has the formula of LD is equals Fy times the reinforcement location factor, which is 1.0, and the coating factor of 1.0 divide the 1.7 times lambda times the square root of Fc prime is equals to the diameter of the steel bar times the diameter of steel bar. So substitute all the given value. So Fy 415 times the reinforcement location factor of 1.0 times the coating factor of 1.0 over 1.7 times the lambda of 1.0 times the square root of Fc prime, which is 28, times the diameter of the steel bar, which is 20. So our development length is equals to 922.68 millimeter. So development length provided 1,200 minus 75 is equals to 1,125 millimeter. So it is greater than LD, this one, so it is okay to use. So summarize in drawing. So our footing thickness is 597 millimeter, and we have the length of 3.1 and the width of 1.8. And our top bars, I mean the bottom bars, we have 11 pieces of 20 millimeter diameter steel bar, reinforcement steel bars, and the outer bandwidth, we have 3 pieces of 20 millimeter in diameter steel reinforcement bars, and so pareho na sila. And the center bandwidth, we have 12 pieces of 20 millimeter diameter in diameter of steel bars. maura na. So thank you for listening.